Hello, everyone, and welcome to this Floatech webinar on databases. So databases for wind are the Floatech databases, your research missing piece. I'm Ines Martorell. I'll be your moderator for this webinar. I'm from Euronovia. We are a partner in the Floatech project in charge of the communication and dissemination activities in the Floatech project. So on today's agenda, short welcome and introduction. Then I'll give the floor to Robert Burns de Luna, who will present the 3 floating offshore wind turbines. Then will be presented the application of the 3 models in real environment. And the third part of the webinar is will be on wave tank experiments, prediction and control validation, and the presentation of some results. From 10:50 to 11:20 will be time dedicated to questions and to Q&A, to questions. So don't hesitate to write your questions in the chat or in the Q&A feature that is made available for you. It's 10:06, so with no further ado, I will give the floor to Robert Burns de Luna from TU Berlin. The virtual floor is yours, Robert. Thank you.
Thanks, Ines. Hello, everybody. I'm Robert. Thanks for the nice introduction. I work here at TU Berlin. I'm a PhD student, and I also work as the project manager of Floatech and am involved in several of the technical work packages. And I will present the first data set, which is composed of three wind turbines. The reason why we do this webinar, maybe to say this in the first place, is to our goal is to have databases that are accessible and that help the community to do whatever they would like to do with the data sets and to help their research. And it can be tricky to take on data sets that other people have been working on and have been composing, and to help you hit the ground running and use databases for whatever you would like to use them for. We want to do this webinar, and since it's going to be on YouTube afterwards, it should help you to really work with the data. So what am I going to present? It's 3 floating wind turbines that can be simulated in cubeLADE. So it's the definition of those 3 wind turbines. 2 of those models have been tuned with respect to experimental campaigns. One of them was the well-known OC5 turbine, and the other one the SoftWind software in the loop experiment. And the third model was tuned in a code-to-code comparison with DeepLine's Wind on the more modern or closer to industry design of the hexafloat substructure. Is this data set for you? Well, that depends basically on if you want to, or if you're using cubeLADE for your research, because if you do, then these are ready to use models that can be applied in any kind of research. So if you're interested in development of controllers or tuning of controllers or testing several kinds of mooring specifications or analyzing the damping, you don't really have to bother setting up new models or tuning them or trying to get them right, but you can just take one of those. And the good thing is we cover a wide range of different floaters. You can just take one of them and start to work on your topic right away. So to next slide, please. So here you have just a render of the 3 turbines that I'm talking about, or that I'm going to talk about. To your left, you see the SoftWind software in the loop model of cubeLADE. This is here with the tower that is replicated from the experiment. This is due to the Froude scaling. This is why it looks a little bit strange, but it's upscaled to the full 10 megawatt that the turbine has. In the middle, you see the hexafloat. This is also the DTU 10 megawatt turbine mounted on a hexagonal substructure. And to your right, you see the OC5 platform with the 5 megawatt wind turbine on top of it. It's a little bit older, but still has a lot of resonance in the research community due to several details, especially with regards to the substructure. So let's start right away with the latter turbine, so the OC5 deep sea wind balanced wind turbine. The link to Tenudo, to this definition, you can see at the top of the slide. So you can just go there, download the turbine file, and import it to Qblade. Things to know about the model. Well, at the top, it's not the NREL 5 megawatt definition that is often used in numerical analysis, but rather an experimental version of that. So it's called the Marienstock wind turbine that was designed and tuned by Coupé et al. And the aim was to reproduce the power, but especially the thrust behavior of the NREL 5 megawatt in experimental conditions in a low Reynolds number environment. It is mounted on the deep sea wind semi-submersible that has been used in several code collaborations in OC4, OC5, and OC6 with regards to uncertainty validation, but also now to more advanced analysis as analyzing the slow drift excitation on these type of substructures. Important things to consider when you want to use this model. So there's basically just one thing. So when you go to the structure file, when you download the turbine and open the substructure.dat file, there is a keyword that's called subhydro constant force that basically applies a constant force to the substructure in the 6 degrees of freedom. And in the experiment, there was in cases without waves, so basically in the decay tests, there was no cable hanging from the top, and this cable had a stiffness applied to the structure. So in decay test, this value in the surge component should be 0. But if you include waves and you want to replicate the results from the experiment, you really should include this force in the surge direction, which is 140 kilonewton. And this is basically because of the cable bundle. But other than that, depending on your application, you don't need to worry about anything with the model. Then on to the soft wind. Next slide, please. So again, the link to Zenodo can be found at the very top. Things to know about it: we have the DTU 10 megawatt research wind turbine rotor and cell assembly at the top. But the tower is basically different because we try to replicate the structural properties as well as the frequency behavior of the tower that is used in the experiment. This information, as well as the definition of the soft wind, can be found in the PhD thesis from Vincent Arnal that he wrote on the entire setup of this software in the loop test bench at École Centrale Nantes. This is a spar type floater with delta connection mooring lines that provide a little bit more yaw stability. And since it is scaled already to a 10 megawatt wind turbine, it may be more useful than the OC3 definition that is out there for modern technology that you want to investigate. Important things to consider: there are 2 different versions on Zenodo. If you click on that link, so one is version 3.x, that would always be the upscaled software in the loop clone that includes the experimental tower definition and also the DTU baseline controller that is applied in the experiment. And then version 4.x is basically the same type of floater, but with different tuning. I think Francesco will talk about that later because we use this for different application, and we're not interested in matching the experiment one for one afterwards. And for these kinds of applications, we needed a more realistic version of the tower. So therefore, in this definition, you find the tower definition that was used in the OO star concept. And if you basically don't want to replicate the software in the loop experiment, but are interested in just using this wind turbine and substructure combination, you can continue to use version 4.x. Both of them will be maintained under this version numbers, and you can find the description of what has been changed if we find further issues with the models on Zenodo. Next slide, please. Yes. The last one is the hexafloat. Again, the Zenodo link at the very top. And then in this case, we have the exact rotor and tower definition from the DTU 10 megawatt wind turbine. And here it is mounted on the SciPem hexafloat substructure. A couple of things to know about this is that it is gravity stabilized, so it has similar characteristics as a spa type platform. So with a very deep center of gravity, and it is transparent to waves because there is only a limited water plane area that is cut by the substructure. It can be assembled in the arbor because you can move this counterweight up and down, and also due to this fact, you can erect it at variable depths. One important thing to consider here is due to IP concerns from the company that designed it, which is SciPem, there is only restricted access to this model. But for research purposes in general, access is granted. So when you would like to investigate something on this model, you can go to the link, and you will be brought to a dialogue where you can enter a message briefly stating who you are and where you're working, and what your goal is to do with this kind of model. And then myself and also Marie-Laure, an engineer from SciPem, will get an email, and based on the individual case, then access is granted. But as I said, for research only purposes, this is generally done. Just to give you a small visual on how it looks like. So you click to the link, you're brought to the Zenodo web page, and to your right, you see the version control. So when you started to work with one kind of versions, let's say 3.0, and in the meantime, we found a couple of things or added some or we modified the model, maybe because some new features were implemented in Kubelet, you can still continue to use the model that you've started your research on, because the DOI will stay there forever. And to your left, you see that we also try um, to detail what changes has been done to the model, so you can decide based on the individual case if it's worth it upgrading to the next version or not. And this is the same for each model. So to wrap up my part, you can find all the turbine files or Kubelet turbine definitions on Zenodo, and then you can import them directly to Kubelet and start to get going. If you don't know how to do that, or if you haven't been working with Kubelet yet, there's a very good read the docs manual page, so you can click on that, and there's a very detailed description. And of course, you're free to reach out to me and my colleagues anytime. And then if you're interested in a much more detailed description of the model and the tuning processes of these three models, there are two technical reports on them, which would be deliverable 2.1 and 2.2. And there's also a preprint that has been published in Wind Energy Science Discussion, where we analyze the behavior of the model and the prediction of Kubelet compared to other codes in much more detail. But as I said, it's still in the discussion phase at the moment. And finally, I think I said that in the beginning. What can this be used for? You have there three fully assembled floating offshore wind turbines, and you can apply your technology to any kind of these substructures. And this, I think, is quite helpful because they differ so much with regards to their characteristics that it can be really helpful to see if one technology works on one platform but not on the other. For example, we in Kubelet, we in Floatech have been using this database already for controller development, where a feed-forward wave-based control that Félicien is also going to talk about was investigated on the SoftWind platform, and wake mixing like the Helix or the Pulse was on OSI 5. Sorry. And with that, Thanks for your attention, and if you have any questions, I'll be happy to answer those later.
I will give the floor to Francesco Papi from the University of Florence.
Thank you, Ines. So my name is Francesco Papi. I'm a research assistant at the University of Florence. I've been working in the Floatech project, particularly in Work Package 2 over the past couple of years. Today, I will present the application of the three models that Robert just presented in the real environment. So more specifically, the data set that we are discussing now is a design load case database for code-to-code comparison. We have a series of simulation results of three floating wind turbine concepts simulated in realistic metocean conditions. This result is a part of Work Package 2 of the Floatech project, which deals with the validation and verification of Kublate Ocean, which is this innovative floating wind turbine simulation tool that has been developed within this project. So the three models that we have in this data set are similar to the ones that Robert just introduced, and we'll get to that in a second, but they are the NREL 5 megawatt OC4, the DTU 10 megawatt soft wind, and the DTU 10 megawatt hexafloat test cases. These three test cases are each simulated with a combination of aero hydroservoelastic tools. So we have Kublate Ocean, of course, and we also use OpenFast and Deep Lines Wind to compare to. This is a validation exercise, so we have code-to-code comparisons alone. We do not have comparisons to experiments. As previously, all the data is open, so we are very proud of this because the whole, in our opinion, the whole tool chain, so starting from input conditions all the way to results, is open, and it really makes you able to kind of reproduce these results, which is really at the core of science. So we are very proud of this, and hopefully it will be useful for your research. Just some examples of potential use cases that I put in here that I could come up to. So code verification, benchmarking in case you implement a new feature in your code, or just development of new floater concepts. You could use this data set as a benchmark. So yes, thank you. So the three floater concepts are shown here. So maybe we should start from the 10 megawatt hexafloat because it is exactly the same as the test case that Robert just spoke about. So that is available open source on Zenodo, and you have the link here. And really, Robert already did a great job describing that. The DTU 10 megawatt soft wind test case, as Robert mentioned, this is again in the link in Zenodo, and it's relative. We used version 4 of this test case within this data set. With respect to the experimental test case, the most notable changes are in the tower definition, which is a stiff tower, which is more suitable, let's say, for a floating wind turbine than what was in the experimental model. And we also did some changes in the floater ballast. The controller is also changed with respect to the experiment. So this is all in version 4 on Zenodo. This test case was simulated in a data set with OpenFast, Deep Lines Wind, and Kublate Ocean, so all three codes. Finally, the NREL 5 megawatt, we used the OC4 configuration instead of the OC5 configuration that Robert spoke about before. So most notably, this configuration has the same semi-submersible, so platform definition, and same mooring line arrangement. But the turbine, so the tower and rotor, is the NREL 5 megawatt reference rotor as defined by NREL, and it is not the experimental rotor that Robert spoke about before. This model is not on Zenodo, but it is available open source. If you go to the cubeblade.org website, it is a test case that is available there. So you can find all 3 test cases if you would want to reproduce these results in Cubeblade. Okay, so as I said, all the data set is available, and you have the link there for your reference. All the information to navigate the data set is available in deliverable 2.3 of the project, and this includes the naming scheme of the outputs that you will find in the data set, the content of each simulation, and the description of the design situations that we simulated. These results are analyzed in depth in deliverables 2.3 and 2.4 of the Floatech project, and also in a journal paper, which is currently in a preprint phase, and which I encourage you to take a look at if you're interested in the results of this part of the project. So yes, thank you. So if you open Zenodo, this is what you would see. If we scroll down to the part where the dataset contents are listed, we have a list that looks a bit like this. Okay, the video went on loop. So we have the actual datasets. As you can see, there are these zipped folders that contain the simulation results. They are pretty clearly labeled, I think, based on the test case and the code. So, for example, the first one up at top is DL for deep lines, 10 megawatt hexa for 10 megawatt hexafloat. In the Excel sheet that you see as the 4th element, we have really all the details about the simulations and the DLCs that are considered in the analysis. And finally, the last 2 inputs over here are wave fields and wind fields, and they are the wind and wave inputs that you would want to use if you want to reproduce these results in your own code. Okay, so coming to each of the data set, each one contains 760 simulations, and they're subdivided as follows. So we have 504 simulations in DLC 1.2, which we use to evaluate fatigue loads. So we are considering, say, a variety of operating conditions that the turbine may encounter during its lifetime. We have 99 simulations in DLC. It's just a second. Let me talk about the list real quick. Yeah, sorry. So we have 99 simulations in DLC 1.3, which is extreme turbulent conditions, 6 and 1.4, which is extreme wind gust with direction change. In 1.6, we evaluate severe sea states. And finally, in DLCs 6.1, 6.2, and 6.3, we have extreme combinations of wind and waves with the turbine parked. So it's a fairly good mix of operating conditions, which can be used to kind of evaluate the operating and parked life of the turbine. The naming scheme of each simulation looks something like the example that we have on the right. So the first element is the code identificator, and this can be deep lines, wind, Cubeblade, or OpenFast. The second element is an identificator for the test case, so 10 megawatt soft wind, 10 megawatt hexafloat, or 5 megawatt LC4. The third element is an identification for the DLC that we are simulating. Then we have the turbulent wind and wave seed number. So all the simulations have a different seed number so that we are ensuring that we are simulating enough environmental conditions to kind of attempt to reproduce the long-term statistical behavior of these test cases. Then we have the significant, the wind speed of each simulation, the significant wave height next, the peak spectral period, the wind wave misalignment. So in these simulations, the wind is always pointing in the X direction. So the waves instead change direction. So we have multiple values of wind and wave misalignment, particularly in DLC 1.2. And finally, we have the vertical inflow and yaw angle of each simulation. Okay, so what does each simulation contain? So the results are in OpenFast binary format, OutB. It's a fairly common format for us, I would say, in the community. If you're not accustomed to working with it, their NREL, which kind of, I would say, uses the format, they're the creators of OpenFast, has made available 2 toolboxes, a MATLAB and a Python toolbox, which contain scripts to read these files. So have a look there. Each simulation contains at least 96 output channels. This include platform motions, control signals, and loads. These are tower, blade, nacelle loads, and mooring line tensions. I said at least because some datasets also contain hydrodynamic forces, and the Hexafloat dataset in particular also contains the tendon tensions that the tendons that connect the 2 parts of the platform. The tensions of those are recorded and stored in the outputs. Again, say this was a quick rundown, but all the details of everything I said, you should find those in deliverable 2.3 and then the Excel sheet on Zenodo. So if I skipped over something too quickly, it should be in there. Finally, how to reproduce these results. So really, how would you use this data set if you're interested in it? So firstly, this is a bit naive, but you need to select the concept that you want to use. And as I mentioned, you can find the Cubeblade Ocean models at the links in the previous slides. You can use Cubeblade directly, which is available open source, or you could use this model to kind of reproduce this model in your own code. So build up the model in your own tool of choice. Once you have built up your model, you need to specify input conditions. So really to do this, all you need is the Excel sheet that I mentioned previously and the wind fields and wave fields that you can find in a data set. This should be sufficient to reproduce the results that are in this data set and that are discussed in the deliverables. If you're interested in the process on how we specified these input conditions, how we got to this list of simulations, that is in another open source data set, which unfortunately we do not have much time to talk about today, but I put the link here. There's a Python tool that allows you to go from raw metocean conditions to inputs for your DLC load calculations. And all of this is discussed in more detail in the open access paper that I listed here, which is also an outcome of the project. So once you have your model, you have your input conditions. Really, all you need to do is choose which conditions to simulate, including the sea state, other variables that do not depend from the long-term representation of the site, such as turbulent density, turbulent seed number, and yaw error. And yeah, you should be set to go reproducing our results. And so I think with this, I have concluded. I gave you, I hope, a pretty comprehensive rundown of the data set, and looking forward to any questions in the during the Q&A.
Thank you very much. Thank you very much, Francesco. I'll give the floor to Félicien Bonnefoy from Centrale Nantes. Félicien, can you hear us?
I've been deactivated. The microphone should work now.
Yes.
So I was saying thank you to my colleagues who were right on time. So we have time to talk about the wave tank experiments that were conducted during the Floatech project at École Centrale de Nantes, where we have developed this software in the loop approach in order to reproduce the behavior of floating wind turbine in waves and wind conditions. Can you move to the next slide? Okay, so this is a very quick overview of the Floatech strategy, the content of the Floatech project. And I must say first that I'd like to mention that this strategy of research at École Centrale originated from Jean-Christophe Gilotto, who started the SoftWind project. You've heard about this SoftWind word quite a lot in the previous presentation. And it was 3 years ago a project that became the name of our software in the loop approach. And Jean-Christophe also started the Floatech project with all these partners before leaving for Inosi company. So let's go back to the topic. So on the left, you have the diagram of the some key point of the Floatech project. Of course, it's all about this Kublai Ocean software, but also you have these controllers labeled here AWM, LWC. While the Kublai software is developed at TU Delft, the controllers are developed, the controllers have been developed at TU Delft, and I want to start with this because that's the origin of the work we've been doing at École Centrale. In order to validate the controller, we have to set some data, to set up some experiments, and that's the key point I want to emphasize on today. Can we move to the next slide? So I'll briefly introduce some aspects of one of the two controllers that we've been testing in Floatech. And this is the wave-based feed-forward control, where the idea is to get some information from the waves and use it to try to influence the quality of the energy production of the floating wind turbine. And this will be done by inputting to the controller the wave excitation loads. Okay, something we cannot measure, but what we can measure is the free surface arriving on the system. And from this, we want to predict this loads, wave excitation loads acting on the system, and use that information to improve the performance of the wind turbine. So this is now laying out in front of us the work we have to do at École Centrale, do some free surface measurements, compute and predict the wave excitation loads, and try to give that as an input to the controller, and that will be exactly what I will show you in the next slide. So if we move to the wave prediction program, it was developed by Inchul Kim, a postdoc in the software, supervised by Guillaume Ducrozet. It's dealing with multidirectional. The wave information that we've measured has been assimilated by a nonlinear scheme, and then we've produced results on how good is the prediction. But maybe before introducing the experiment, I want to show you the basic ideas of the system. So on the top left, on the top right, sorry, you have this diagram where you see the device, a sensor that is measuring the wave field. It will be a radar, a LiDAR, a camera, whatever, and it's measuring at some points, scanning the free surface and measuring wave elevation at a set of points. And from this information, we want to compute and predict the wave elevation at the location of the wind turbine. And more exactly, we will talk about that later, we need to predict, again, the wave excitation loads at that point. So if we move to the next slide, we'll see the experimental data system that we set to mimic that radar, LiDAR, camera measurements. On the far right, you see a diagram with the setup of probes we've been using. So all the probes are aligned on a network that is a linear array of probes that have been rotated several times. And by reproducing the same wave again and again in the tank at a different direction each time, we can gather all the data and get this scanning of the scan of the free surface in front of the floating wind turbine. Okay. Next, some words about the database itself. So if you go to Zenodo, you've seen before with my colleagues a list of different database for simulation, for deliverables, etc. And in Denodo, you can access the list of all these deliverables very easily if you use the Floatech community. If you search for Floatech community in Denodo, you'll find a total list. Okay. So regarding the validation of this wave prediction, you have a list of records. All the C-states that have been tested are centered around a strong C-state, 12 seconds, 7 meters per second, that have been extracted from the Live 50+ project at the west of Barra test site. Okay, this test site is documented in Live 50+ results, and that's how we extracted that, which shows this strong wave conditions in order to obtain strong motions of our SPAR platform. And it has been also tested at different levels of nonlinearities by varying the significant wave height, and also different values of the directional spreading. Okay, if we move to the next slide, then you see on the screen an example, a sample of the test. So it's the very few waves that arrive that are generated in the tank. So at the beginning, now you see quite long waves, it's quite smooth. And if you wait a little bit, and we'll see some shorter waves also arriving from the wave maker and finally reaching the probe array. So again, this is a collection of different runs. We have worked a lot on the repetition of our wave maker to make sure that the data we are producing here is accurate. And so it was a good point for us to work in this project because we have to improve our test procedures. And each of those tests, I forgot to mention, that is 2 hours long at full scale. So maybe we can skip the video, and we don't want to see that during 2 hours. Okay, if we move to the next slide, we'll see that we also had some measurements. And sorry, the title of the right figure is in French. Forgot to translate that. We also had the opportunity to actually measure the wave excitation loads on our SPA platform during the Flower HP Flow campaign. So it was not initially something planned in the Floatech project, but that's something we could do, and that's very useful for the Floatech project. So in this campaign, a very stiff structure was maintained in the tank, and in the middle, in this center picture here, you see the model itself, the SPAR model, attached to this rigid structure by means of a load cell. And the load cell can give us all 6 degrees of freedom loads on the system. And we played again the same waves, so we could have a direct measurement of this excitation force. In the, I forgot to say that, but in the wave prediction, if we move backward, please. Let's stay on this one for a bit longer. During the wave prediction, some effort was done on the wave excitation loads prediction, because that's what we need. And on the right, you have a comparison between measurements and prediction. Measurements are in red and prediction are in black. And you can see that you have a very good match, at least for the frequencies where we have a lot of energy. So in terms of spectrum, when we are close to the peak of the spectrum, we have a very good match. And maybe some high frequencies are not so well predicted, and you have some discrepancy, but it's always like short periods or short waves. Okay, now we can move to the following slide. So all the previous database was experiments for wave propagation and force prediction. And now this one is another application, directly a full-scale measurements of the wave field and prediction. So first, before going any further, I want to mention that unfortunately, because it includes the work of a private company, this database is embargoed for 2 years. So data will be available only in 2 years from now. The content of the database is a synchronous measurements of all conditions at test site. So waves, wind are measured exactly as a test site. Current is given from tidal currents prediction, and the data are synchronized, and they are gathered in one single package. That's the originality of this work. As you can see in the picture in the middle, you have a radar that was mounted on the Floatech wind turbine, the one that is installed on the SEMREV test site from the OpenSea Institute. The radar was installed during 1 year, and some images was captured by the radar. This is not part of the database. That's the second point. The raw radar images are not part of the database, but the result of radar-based prediction is also included in the database. Okay, so maybe we can move on now. And the final target of the work package 3 regarding experiment in a model scale was to validate the wave-based feed-forward controller. So we had to use our software-in-the-loop system that is explained here briefly. So it's a coupling between a simulation of the aerodynamic part of the problem in order to provide a correct estimation of the aerodynamic loads to the actuator that is installed instead of at the place of the nacelle. And this actuator will generate the computed loads in order to exert on the model the correct load at the correct position. And then the floating wind turbine model inside the tank will have waves arriving on the system and synchronize wind loads by means of the actuator. New feature was developed during the Floatech project. The actuator itself is now equipped with a force feedback. That's the work of Rasoul Modjadizadeh that has been employed recently. It's an implicit sliding mode controller that proved very efficient. I'll show you some details. The position that is given to open fast of the system and as well the velocity has been improved by using a new way to compute the velocity. It's what I call differentiator on this graph, against the work of Rasoul. And also the actuator itself evolved from one component to a 5-component system. Because it's all about experiment, maybe we can move to the next slide where we'll see some picture. Okay, I couldn't prevent to show you a picture of the system. So on the left, you have the floating spar inside this wave tank. You have this flexible mast. I'm not talking too much about the mast today. And then at the top of that, you have this actuator system consisting of 2 sets of 3 motors. One is for the thrust. One set is for the thrust and 2 moments. And the second set is for the torque of the generator and for the 2 remaining forces. Okay. If we move to the next slide, maybe we have time to watch this video. We're almost done. If you can start the video. Okay, so I'm confused because during webinar and Teams, sometimes the video are not showing nicely, and well, okay, the quality is very poor. Sorry about that. At the end, we have some detail about the system. So now we move from the floater itself to the top nacelle. So we've seen the spheres that are used to measure the position. We've seen the Wi-Fi antenna to transfer the data. And I will finish briefly the presentation with some experimental results. Okay, so if we move to the next slide, please. Okay, so very briefly some results. On the left, you have the open loop system without the step-back controller. On the right, you have this the closed loop response. On the first line, you have the 2 signals, so it's the same wave field played twice. So it's almost the same. It's the same waves and wind played at the same time. First line, you have all the frequency components. It's the raw signal, and then on the second line, it's only the low frequency range. Third line, only the wave frequency range, and the last line is the high frequency range above the wave frequency. So it's what we call the 3P range in our case. And you see that when we compare the left results to the right, that reference in blue and measurements in red are much closer with the closed system. So that's something we could improve. And that's shown here just for the thrust, but the 4 other force components that are controlled are okay, also okay. So if we move now to the last slide, maybe we can switch. This one is the same data, but in the Fourier space, in frequency domain. So we can move to the next one. Okay, the database. This database is due by the end of the month, so it will be published soon. Again, if you follow the Floatech community on Zenodo, you will find the link with the correct DOI and the correct link. It will be published probably next week. It will contains for all multi-directional waves that we've tested with in the case of the wave prediction database. We will also give you the motion of the wind turbine and also add the wind experiment. We will produce the results of the wave-based feed-forward controller. It contains almost the same measurements Francesco was mentioning. It's a big list of parameters we have. The same turbine data that we have in the simulation, because it's also simulated in our case, we have it, and we have also all the measurements from the wave tank. Okay, so this is it, I think. Thank you for your attention.
Thank you very much. Thank you very much. I'll just so now we have time for the Q&A. I'll look at the chat, so maybe if there are any questions. We have no questions. We have no questions. Oh, we have a question from Ana Isabel Martos Barba. You have the floor. I'll authorize your microphone. You have the floor now. You can, yes.
Hi, morning. How are you? Thanks for the information. Well, I'm a wind resource analyst, and to be honest, we don't know yet how to deal with the losses associated to this kind of projects. So I would like to know how the project is addressing the future losses that this kind of system will have in the future.
Francesco, Félicien, Robert, would you like to answer this question, or maybe need clarification?
I think I would need a little clarification. So what is meant by losses?
Well, I mean, not only wake losses, but future availability losses and transmission losses. This kind of in our work, we have to address several kind of losses when we plan a wind farm, a future wind farm, and we are starting to work now with floating wind turbines. So it's a huge amount of information we are missing now. So these kind of projects are really helpful to us because we yet don't know fully how to address this kind of losses we will have in the future. So I would like to know how the future is addressing the energy and the performance losses that the system will have in the future.
Thank you. Is it? Yes.
I can try to answer. Yeah, that's a very good question. Unfortunately, and then Robert and Félicien can jump in if they want, we didn't really address that in this project because we didn't do, to my knowledge, any analysis at a farm level. So all the analysis in this project, they're concentrated on a turbine level. So let's say it goes without saying that we didn't really go into wake losses. I think there's something minimally in work package 5, but it really wasn't the main focus of the project itself. And we didn't also go into the array cables and installation issues and that whole world. So yeah, I hope that answers the question. Basically, we didn't really look into that in this project.
Thank you for your answer. Do we have any more questions? Don't hesitate to raise your hand or to write your question on the chat. No particular questions. Just gonna check the conversation. No here. Q&A. No. Okay. Are you sure? It's the perfect time to ask questions. You have 3 Floatech researchers with you, so don't hesitate. Don't be shy. Okay, so if we don't have any more questions, I mean, we can end the webinar now. This webinar was recorded, so we'll send you the link to the YouTube video, and it will be published on YouTube as well. So you'll find all the relevant data that was showed today.
One final addition, Ines, maybe. So if you've been following the Floatech project in general, and if you would like to get in touch with the researchers that are working in this project, we will have the final info day on December 1st in Berlin. This will be very much in the city center, and we'll release some information on it shortly, such as the agenda, who's speaking. We'll have a panel there, hopefully with policymakers as well as people that are directly involved in the decision making to advance this technology. And this event is open to anyone who's interested in this topic. So if you would like to participate in this event, just click the follow button on LinkedIn, and and we'll inform you shortly about how to register and so on, and we'll be very happy to talk to you there in person.
Yes, thank you, Robert. Really important information. So December 1st in Berlin, the Floatech final info day. I'm gonna stop sharing my screen just to check if we have any more questions. No questions. So thank you very much. So check your email soon, because we'll send you the video of the recording so you don't miss any information. Thank you for your attention. Thank you to Francisco, Felicia, and Robert for your hard work in preparing this webinar. And I hope you had this was useful for you, and see you on the 1st of December for the final info day. Thank you very much. Goodbye.